Radical bromination and UV Viz will be on the final exam. We'll boil it down to take-home messages. Final exam is Monday, I believe, at what time? 8? Used to always be at 7, but they changed it. 8 o'clock, is that right? Right here, Monday. Okay. 2-hour exam. It'll be just similar format to test. It'll be sort of like 1.5 tests. It'll be about 7 to 8 pages long, maybe. If you go back and bottle up what you knew the day of test 1, test 2, and test 3, then you should be okay. Test 3 should be fresh, although it doesn't mean a lot. Test 1, hopefully if you look back now, you'll see that it was not overly difficult now that you've been working with organic chemistry for a couple of months. Acid-base is important. Test 2, I would always say is probably going to be required the most review because of the alkene reactions, the stereochemistry, and it's been 6 weeks since we were covering that material. Alkene reactions, actually I'll send out a fresh copy of the alkene puzzle. That's a good review. The alkene reactions, although they're not all there, 90% of them are. One that is there is radical bromination with HBr and peroxides, which we'll mention today. Again, very similar format on the final exam, nomenclature, short answer, multiple choice, predict the product, reagents, mechanisms, and spectroscopy, IR, and mass spec. And we're going to look at UV Viz spectroscopy today. It'll be short and sweet, hopefully. Trying to find an alkene puzzle. Anybody have it handy? Alkene puzzle. Any questions about final exam? I'll offer a review session on Thursday and Friday at 2:30 during the regular lab time. Hopefully you're free, optional, and there are review questions in the workbook. I believe the answers are there now. I used to didn't have the answers there. We can go over anything like in the test, anything you'd like. Thursday and Friday at 2:30. Anybody have the alkene puzzle? Yes, thank you. HBr and peroxides. HBr and peroxides. We looked at alkene with HBr. What about alkene with peroxides? We never looked at that back with alkene reactions. But it was certainly here, number 17. What's going on there? That's on the handout we were looking at. Let's finish that up. Radical bromination. And that's here at the top. But before we do that, let's pass in the lab answer sheets. If Thursday lab, we'll pass them in first. Thursday lab. Any other Thursday lab? Okay, Friday lab. Friday lab. Okay, let's look at this here. Anti-Makarnikov addition of HBr. That's the heading with some review. Remember alkenes, we can hydrate the alkene, we can get such an alcohol, we can hydrate it with aqueous acid, or we can hydrate it with the two-step process of oxymercuration followed by reduction. Either way, that's a Makarnikov hydration. We covered that. That should be clear, maybe with a couple of minutes looking at it for refreshment. That should be clear. We can do an anti-Makarnikov hydration with BH3 followed by a magic step of oxidation. That gives the primary alcohol in this case. We covered that. HBr, hydrohalogenation, hydrobromination. Alkene attacks H+, leave cation here. Bromine or bromide attacks cation. We get this product. How do you get the product with the bromine on the other carbon, which is analogous to getting the hydroxide or the hydroxyl? Hydroxide is OH minus. It's not hydroxide, it's hydroxyl. On the far carbon, how do you get the bromine on the far carbon? We never covered such a reaction. But it turns out you can do this just by putting in peroxides. A typical HBr with peroxides. Now typical, that's like hydrogen peroxide is used, but it could be any peroxide, like benzoyl peroxide. And the peroxides makes it go radical reaction. So this up here is an ionic mechanism involving ionic intermediates. This involves radical intermediates. It's a radical mechanism. And it turns out you get the anti-Makarnikov addition of the HBr. There's a new H here. Now you could just memorize this reaction. Okay, what happens when you put 8 peroxides into the HBr? You get the reverse stereochemistry. You get the anti-Makarnikov product. There you go. Okay? We can look at the mechanism. So it's the same reaction here, HBr and peroxides. What is the mechanism? Let me get the bromine over there. Well, what happens is, this apparently happens real quick. And the peroxides causes this to homolytically cleave. I'm not going to look at the full mechanism and how it promotes it. You might also could do light. Light may make this homolytically cleave, but peroxides is more common with HBr. And this is going to give H radical plus Br radical. Okay, I don't know, something doesn't seem right here. At this point, we have an alkene here, not an alkane. I mean, we have alkane carbons over here. We'll have to talk about this because if you think about these reactions, they can be very confusing. What are we actually doing here? Alkene chemistry versus alkane chemistry like we did on Monday or last Friday. We'll go back and summarize this. Because it can be very confusing and you ask, well, why do you get the outcome there and there? It's ultimately all based on thermodynamics. But what you end up getting here, and how we get this, forget about anything else, how do we get that there? We need a bromine on this far carbon. We got the radical. What happens is one of these electrons teams up with one of those electrons. Now, if one of these electrons teams up and makes a bromine bond, there's going to be one electron left. And we're going to have a bond. Well, it turns out you would rather have the bond to bromine there and then the single electron left here. That is, the other electron moves and sits on the carbon. One electron teamed up with bromine electron, and you get to this. But if we went the other way, we would have gotten to that. That is, if the electron went this way and teamed up with bromine, and that electron went over here. Well, sit back and look. Which one of these is better? A radical is just like the carbocations, electron poor. Would you rather have electron pour this carbon or this carbon?
Tertiary.
Grant?
The right, tertiary.
This one, tertiary, just like a cation. You'd rather have the radical here. So this is the way it goes. And indeed, you get the bromine on the outside carbon. It all comes from the fact that the alkene attacks the bromine radical. Now, one thing you could ask is, well, why doesn't it attack the H radical and you get an H here? Then the H would be there instead of over here. Well, that's the thing I said. It's kind of like, well, why? It's largely driven by thermodynamics. And you can always question it, but this is the outcome. And we're going to propose and show a mechanism for that outcome. Now, how do we get final product? We've got to get an H on here. Well, there's H radical. That radical could capture this radical, and we can have a CH bond. That would be the product. But then that would require us to do this again. And actually, you don't have to have but a little bit of peroxide. Typically, when you do radical reactions, you want to show them propagating. So the initial step, we didn't label this as initial last time, but this is initiation. Once you get your radicals, you initiated it, then you should not have to initiate anymore. It should self-propagate. That's typical for all radical reactions. For most all, they self-propagate. At this point, we can self-propagate by, instead of reacting with H radical, react with HBr. And we can say this electron teams up with the H electron, and it comes here. And the other electron goes there. What does this arrow movement give? Electron teaming up with H and electron would be an H, 2 electrons, and make the bond. But what do we also produce?
Br radical.
We produce Br radical. And so now the Br radical can come back up here, and we can start just cycling over and over and over. And you don't have to initiate anymore because the reaction produces Br radicals. And that's called propagation. So we get this cycle. And theoretically, you only need one initiation. But you get the bromine on the outside carbon because you want the radical formed here. And the radical captures the H. It starts by the alkene attacking the Br radical and giving this, not this. So this is where your regiochemistry comes from. But at the top reaction, up there, what does the alkene attack? All you got is H plus Br minus. And we can show that like that. We can also show it covalent. You can't show both. Okay. Now, the alkene attacks H plus, or we can attack H and move these electrons here. In terms of mechanisms, I see a lot of mechanisms that are just very nondescript. We see something like this and then something like this. This arrow does not mean anything, much of anything. What does it mean? I don't know what it means. This arrow means these two electrons are pulling away from the H and moving on to the bromine. I don't see that in this arrow. You need to work on clarifying what your arrows mean, because if you can't show what they mean on paper, I don't believe you know what they mean in your head. So you would want to draw this bond in and do it more precisely. But this leads to an H out here and a cation here. So we get an H on the outside carbon. Then the Br minus ends up attacking here, and that's how we get our old-fashioned product like that. Down here, the alkene attacks the Br radical. What's common is electron 4 carbon tertiary, electron 4 carbon tertiary. So a little bit of mechanism, but in the end, just like many reactions, there is some memorization. People say you can't memorize organic chemistry. Well, you can a little bit. There has to be more than that. The memorization prompts you. You memorize reagents, but you have to then understand reagents. You memorize an outcome. Okay, antimarker. What does peroxide do to HBr reaction? Gives you the reverse regiochemistry. That's it. Okay, and there's an example on that puzzle. I'll send that puzzle out again so you can have a fresh copy. So this is a reaction that some of you asked about 6 weeks ago because it's usually in the alkene chapters, but I sort of delayed it till now. We can throw it in at the end. So, products here. These are the products of these two reactions. And then we'll look at UV vis. Okay, the top one here. HBr, hydrogen peroxide, antimicrobic addition of HBr. New H down here, the bromine there. We had an HBr across the pi bond, but it's reverse regiochemistry from our standard regiochemistry. What's going to be a relationship between the methyl and the bromine? Cis or trans or random? It's actually going to be random because whenever a radical reacts, you get an outcome just like a carbocation reacting. It's going to be from either side. There's no back bonding, there's no backside attack. It's going to be random cis-trans. Both carbons are going to be racemic. There's no defined stereochemistry in any of them. You're going to get how many, okay, here we go, final exam. How many possible stereoisomers for the product? Four, right? Okay, next reaction. HBr, 2 steps. Totally different, okay? You do this one 1 week, and then you purify your product, whatever, and then you come around and you do this one the next week. Okay? I'm just combining it. Instead of showing 2 line reactions, I'm showing 1 and 2. Okay? But we discussed that 6 or 7 weeks ago when I showed you line reactions. Okay, what does the first thing do? Well, that's antimicrobic addition of HBr, right? Boom, 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 boom. So which carbon's the bromine going to be on? End or the second carbon? Right? So that's 1. Okay, what would KCN do to this guy? Yes, we have cyanide, good nucleophile, SN2, and so we can get boom, 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 boom. That's not it. 1, 2, 3, 4, 5. 5 carbons. 1, 2, 3, 4, 5. 5 carbons, and then the nucleophile. So that's number 2. Radical antimicrobic addition of HBr to the alkene, and then that's a good old SN2 reaction. Okay, that's the radical reaction. Any questions about that before we move to UV vis? Okay, UV vis, that's a caret, and this is a UV vis instrument. It looks about the size of an IR. Light source, very similar idea to IR, except an IR uses IR light. Here we're going to use a combination of ultraviolet and visible light. So these two regions of the electromagnetic spectrum are grouped together into one spectroscopy. You do have to review and know your electromagnetic spectrum. Which is higher in energy, UV or visible? UV, because it's the UV rays from the sun that are the most harmful, not the visible light from the sun. Okay? What does IR fall compared to those? Stronger or weaker?
Weaker.
So you need to know that type of stuff. Does UV have a longer wavelength or shorter wavelength than IR? Shorter, et cetera. Okay? So that's just review. Now UV is typically, UV vis, we typically give the value of the light in nanometers. And UV is about 200 to 400 nanometers, and the visible spectrum is about 400 to 800 nanometers. And we always list nanometers. What do we use in IR? What do we list on your x-axis? What units are the numbers?
1 over centimeters.
Inverse centimeters, yes. And centimeter, would that be a wavelength or a frequency?
Wavelength.
Yeah, so that's a wavelength. Okay, but it's inverse. And so that you get a number. What do we call that number after it's been mathematically manipulated? Like 3,000. Is 3,000 a wavelength, or what is that?
Wave number.
Carbonyl at 1720. 1720 reciprocal centimeters, but what's another name for that?
Frequency. No.
It's called a wave number. Also known as a wave number of 1720. Okay? It's reciprocal. Well, here you don't do any reciprocal. Okay? It's just typically listed, and it's nanometers. Where that over there was centimeters. Which is longer, centimeters or nanometers? Centimeters, right? Longer. Okay? IR has longer wavelength. Lower energy. So all that you need to review and refresh, etc. Okay, example of electromagnetic spectrum. Compared to IR, well, it's much simpler. And also, basically we have absorbance here and then wavelength in nanometers. In IR, basically the flat line's at the top and we have peaks that come down, right? That's essentially absorbance. Here the flat line's at the bottom and we have absorbance going up. So it's like it's flipped. But it's also a lot simpler. IR, if you just flip it over, you got peaks all over the place, right? This is just sort of one. What we have here is we have a point of highest absorption. Absorption, right here. That's the highest point. And that highest point, we can come down and get a wavelength. And the wavelength for this is about 217. Right there, 217. Now this is for butadiene. And the point of highest absorption is called the lambda max. Lambda being wavelength. That's the point of maximum absorbance. 217 nanometers. Now that we know that, that can become a physical constant. Just like a melting point, just like a density, just like a refractive index. You can say, hey, the lambda max is 217. For example, if you have an unknown and you think it's butadiene, you could run a UV vis and you can see where the lambda max is. If the lambda max of your unknown is 290, then it ain't butadiene, because we know that butadiene has a lambda max of 217. Basically, all this is absorbance. Right here is absorbing light of, okay, right here. Does this molecule absorb light of 220 nanometers? Yes. Absorbs that much. But it absorbs more over here. Now, does this compound absorb light of 300 nanometers? Pretty much no. There's no absorbance here. What about less than 200? Does it absorb at 180? Probably why, Glenn?
Probably yes.
Why probably?
Because you cannot see it, but...
Because if you continue
the
this
tendency-
line,
yeah, the tendency
you're
is-
saying it probably doesn't just magically drop off?
Yeah.
Okay, why don't we plot it here?
It's not UV light. Is it not UV light anymore?
You're saying that because we said UV was 200 to 400? Yeah, it's 200 to 400, yeah. It's actually UV, but it's called vacuum UV. It's listed somewhere. What did we say? UV 200 to 400? That's actually not correct. That is the UV that we scanned. 100 is still considered UV. That's considered vacuum UV. Why is it vacuum? It's because you don't typically scan like at 150 or 180 because oxygen absorbs heavily here. And actually, Vlad, if we did plot this, it would come over here, it'd be a huge absorbance. But it wouldn't be for this to compound. It would be for oxygen that's present between the compound and the absorbent or whatever. You're going to get an oxygen. Now you can run the UV and get only the compound absorbance, but you have to get rid of the oxygen. How would you do that? Do it with a vacuum. Suck out the oxygen. That's much more complicated. Usually the instrument's more costly. It's not as common of an instrument. So it's difficult to get a UV absorbance of your compound down here. Oxygen will absorb down here. Okay. Now what's going on when we absorb UV light? In IR, what happens? The bond is stretching, minding its business. Here comes some IR. Show me some IR. I absorb it and go to a higher vibrational level. Higher energy vibrational level. And that's sort of the discussion of how the absorbance takes place. How does the absorbance take place here? Well, here it involves exciting an electron to a higher level. When we do this, we don't say you excite an electron, we just excite the vibration. Here you actually excite electrons to a higher energy level. Now there can be a variety of excitations, a variety of electrons, and this shows them. You can have sigma electrons, those are ones that are making sigma bonds. You can have pi electrons, those are ones making pi bonds, or in p orbitals. And you can have lone pair electrons, which are not making any bonds. This shows the different excitations and the energy gap between the lower level and the higher level. N would be non-bonding. For example, you can promote a non-bonding electron to a pi star orbital. What are these star orbitals? Okay, we've never talked about molecular orbital theory here much. We may have touched on it in Gen Chem. We've only just been doing valence bonding. But we've never talked about molecular orbitals. Now, I'm afraid to ask you if you cover this in Gen Chem because when I took Gen Chem, I know we did it. I don't think you guys do it anymore. So I would ask for your money back. But when you talk about molecular orbitals, it gives you the excited state orbitals. Ground state versus an excited state. And now if you have the theory that they're there, and the theory has to be supported by some experiment, right? Then you can say, hey, I'm going to excite an electron to this excited state orbital. It takes energy to excite it. Where does the energy come from? The molecule absorbs the UV and that promotes the electron. Okay? I'm not going to spend much time here, but different excitations. What type of electron do you think is easier to excite? A bonding electron or a non-bonding? Non-bonding electrons are easier to excite. So lone pairs are the easiest to excite. That's why it turns out that the non-bonding lone pair and the pi star is one that's lower. That's a lower energy gap. Mainly because these are non-bonding electrons. The most difficult transition is this one. Highest energy is required. This is energy difference. Well, what type of electrons are these? Sigma bonding. Which type of electrons are held tighter? Sigma bonds or pi bonds? Yeah. See, these are held so tight, and they would, the excited is takes a lot of discussion. But the main thing is a sigma electron is going to take a lot of energy to excite. And this is really energy, right? You can turn all this into energy. Now let's go back. Which is higher in energy, 200 or 300 nanometers? It's a wavelength. Shorter wavelengths, higher energy, right? Higher energy. So if we were going to correlate these two to light and say one of these occurred at 200 and one of these occurred at 300, which one would be 200 nanometers? This one, because it requires more energy and 200 is more energy. Let's try to get to a take-home here. Most of the peaks that are beyond 200 are not these. These require too much energy. These typically occur in the vacuum UV, below 200. The ones that are going to occur out here and into the visible are going to be the easier ones because this is lower energy. Like into Pi star. But actually, that's actually the easiest, but it turns out to be weak. The most important, the most intense, and most important is pi to pi star. It's weak enough that it's going to occur out here, but it's also going to be the most intense. And we don't have time to explain why it will be the most intense. But pi to pi star, and this is probably a pi to pi star transition. Does this compound have pi electrons?
Yes.
Yes. At 217, that is the optimal frequency for exciting those pi electrons. And at 217, the molecule, ooh, I really like that, and it absorbs it and it excites. Now at 225, it excites some of them too, but it just, I'll excite, I don't like that energy, I don't like that wavelength too much. Compound really likes 217. And the pi electrons are being excited. Now, does this compound have sigma electrons? Yeah, there's many sigma bonds there. Those electrons can be excited, but it's going to take energy and light over here. And guess what? We're not even plotting them for reasons already said. Pi to pi star is usually the most important. Here's another example of a UV vis. We will boil this down. This compound. This compound actually has sort of two spots where it looks like there's some absorbance going on. Right here, which is what? About 240? Yeah. Here's your lambda max, the maximum absorbance. But if you look right here, there's also a little ridge. It's like something else kind of happened here. This has been ascribed to a pi to pi star transition. Pi electrons excited. Right here, the lone pair electrons are being excited on that oxygen. Like we said, the excitation of lone pair electrons does not give as intense of a peak. Your more intense peak comes from what? Pi to pi star transition. Does it make sense that the peak for the lone pair transition is a longer wavelength, which is lower energy? Yes. You don't need as much energy to excite lone pair electrons. They were excited here. Remember, everything in chemistry is usually quantized. You're like, well, 200 is high energy. Why doesn't that excite the lone pair electrons? Because it's quantized. It doesn't get excited until the exact energy that is needed comes in. Okay, pretty nondescript in a way, but it does give us some information that we can use. Look over here. Here's beta-carotene. Where do we find beta-carotene? Refer to page 1. Yeah, carrot. Here's its UV vis. What do we see about the lambda max here compared to other here? Peak of highest absorption is what?
440.
About 440, which is now into what region of the spectrum?
Visible.
Visible. Does this guy absorb in the visible? Well, it looks like it doesn't, we don't know if it tells in there or not, but okay, that's all UV. This has tons of absorption in the visible. Because look, here's visible. Lots of absorption. Before we answer that question, why is beta-carotene orange? This compound's colorless. Why is beta-carotene orange? Why has it got color?
It absorbs the everything.
Because it turns out, yes, if something absorbs in the visible, now it doesn't absorb all visible, it's just absorbing some. And if you remove some from visible, from white light, what are you left with? You're going to be left with some color when you remove something out of white light. Turns out you're left with orange. Now, does beta-carotene absorb orange? Actually, no. It's not absorbing orange. From 400 to 800, where would orange fall? You remember Roy G. Biv? Were y'all told Roy G. Biv? Remember the light spectrum, colored light spectrum? Red, orange, yellow. Is red 400 or 800?
800.
Yeah, red is actually 800. What's after red?
Infrared.
Infrared. Infrared. There's Roy G. Biv going this way. So of Roy G. Biv, what's the highest energy color? Violet. See, violet is here. What's after violet coming this way? Ultraviolet. So it's violet to red. But if you look at that, orange is actually over here. It's not absorbing orange. It's actually absorbing blue. And if you absorb blue light from white light, you're going to appear orange. Now, how can we tell what's it absorbing? What do you get? The color wheel. Let's jump to it. You turn over. Now, this is in black and white. If you can get this in color, what happens is beta-carotene is absorbing largely at 440, which is actually blue. If this was colored, that'd be blue. It's absorbing that. The color you reflect and that you will appear is the opposite color. And if you go across through the middle, you'll see that the opposite color is orange. So you can make use of a color wheel. So, carrot is orange because beta-carotene, and there's other pigments. Pigment is a term for a molecule whose color absorbing light. And if you're an art student, you might be interested to know how colors originate and how the molecular structure of different molecules can give you different color. And there's actually some research that people try to develop new colors by developing new compounds. Question?
Oh yeah, I was just thinking, these molecules that absorb like UV rays, would they be good sunscreen products?
Yeah, that's what a sunscreen does. Yeah, of course. I don't know if there's a handout in here, but if you look up sunscreens on Wikipedia, they'll give you a whole discussion of it. Yeah, exactly. Sunscreens are molecules that absorb UV. The electrons get excited. What happens after that? I'm not going to talk about that. Where does the energy go then? Does the electrons just stay excited? No, the electrons can fall back down and the energy comes out in some different ways. The most common way would be heat. Okay, so we turn light into heat through this mechanism. But there may be other ways for the electron to decay back down to ground state. Okay, why is the lambda max shift towards longer wavelength? Okay, it happens because of conjugation. See all this conjugation? You have 11 double bonds conjugated. The more conjugation you have, the more it's going to shift the pi to pi star transition, which is usually your lambda max, Thus, the more conjugation you have, the more the lambda max will be shifted to the longer wavelength. For something to be colored, it typically has to have about 3 to 4 to 5 bonds conjugated. This molecule over here only has 2 pi bonds conjugated. 2 pi bonds is usually enough, not enough to get it absorbing into the visible, and usually such a compound is going to be colorless, like water. It will reflect white light without absorbing any, and it will look colorless. Compounds that are highly conjugated will absorb into the visible. Why? We'll try to boil this down as we approach in the class. The more conjugation you have, this is a simple example. Ethene versus butadiene. For structure, this is just one double bond, where now we have 2 double bonds conjugated. The more conjugation you have, the smaller the energy difference is between your HOMO and LUMO. Said here, HOMO, what does HOMO mean? Now, serious question. Did y'all see HOMO and LUMO in Gen Chem? Okay, I don't like that at all. HOMO means highest occupied molecular orbital. I have electrons here. LUMO is lowest unoccupied molecular orbital. It's unoccupied, but it's the lowest one. And typically, everything going on here, an electron is excited from the HOMO to the LUMO. But the more conjugation you have, the smaller this gap is, and thus the easier it is. And as it gets easier, it requires less and less energetic light, thus longer wavelength. Something with a gap real small is going to require very weak light. Okay? Strong energy will no longer do that because it's everything quantized. Beta-Carotene, very conjugated. Okay, let's see if we can finish this up, boil it down. It's the type of question you might see in a testing format. Rank these from highest to lowest expected lambda max. Which would you expect to have the highest lambda max? Now this refers to wavelength, not the most intense, but the longest wavelength lambda max. Which would have the longest wavelength lambda max?
The third one.
This one. 1, because we have 3 pi bonds conjugated. Where over here we only have, well, what? Which one would be second?
This middle one.
Why the middle one? 2 pi bonds, 2 pi bonds.
It's always conjugated in the
They're
middle.
conjugated here. This one you have no conjugation, so that would be 3. What if I said this? Of these, 2 of them are colorless and 1 of them is pale yellow. Which one would you expect to be pale yellow?
The conjugated.
Number 1, because it's more likely to absorb in the visible compared to the others. Now I suspect number 1 is probably colorless, but I doubt it absorbs in the visible because usually it takes a heteroatom. Just simple carb alkenes is probably going to take 5, 6, or 7 pi bonds. Okay. As you advance, you learn more about how structure can affect UV-Vis. Here we go. You remember this? It's transtylbene dibromide. Which would you expect to have the highest lambda max? There's more conjugation. Here, the double bond makes the whole system conjugated. Now, neither one of these carbons have p orbitals. 2 separate pi systems. Extended conjugation, higher lambda max. Actually, this compound has a very hint of yellow to it, where the dibromide typically is pure white. You can look here. UV-Vis. Whenever we look at spots on your TLC, the compound has to absorb UV to see them. Now there's also a dye on the plate, but that's where you've used UV before. Okay, we're about out of time. We're out of time. This is the take home here. Okay? More conjugation, higher lambda max. Now, application, you can look on the back page. It talks about sunglasses that when you go outside they darken. Anybody ever seen these? Okay. The back page talks about that. There's actually some organic compounds in the lens. And when it's exposed to UV, the molecule actually, you can do chemistry. The UV can cause chemistry to occur. So that's just an application. Wish we had 10 more minutes, but the take-home message